So now we're looking at mass spectrometry and time of flight mass spectrometry in particular. So time of flight is a version of mass spectrometry that AQA focuses on, and you've just got to be aware of this, because if you do a search online for mass spectrometry, you're quite likely to find other versions of mass spectrometry, ones that employ a slightly different technique, although they're fundamentally measuring exactly the same thing. You will find different descriptions of how the mass spectrometer works, and you've got to be very wary of that. So you must make sure that you're definitely always looking at a resource that is focusing specifically on time of flight mass spectrometry. So back at GCSE, you looked at isotopes, and you discovered that isotopes were atoms of the same element. So they had the same atomic number, but they in fact had different mass numbers. So that meant they had the same number of protons, the same number of electrons, but they had different numbers of neutrons. The discovery of isotopes really stems from mass spectrometry. So mass spectrometry was a way of discovering them, and it's been a way of definitively identifying them, i.e. Does a particular element have isotopes, and if so, what isotopes does it have? So we know that carbon has 3 isotopes: carbon 12, carbon 13, carbon 14. And the other thing that mass spectrometry was able to determine was the relative abundance of these isotopes. So again, thinking back to your GCSE, you might remember that chlorine on the periodic table that you had a mass number of 35.5. And that was because chlorine existed in 2 forms, or 2 versions of chlorine, 2 different isotopes. So there was chlorine 35 and chlorine 37, and 75% of chlorine was chlorine 35, and 25% of chlorine was chlorine 37, and that's why we had an average of 35.5. So mass spectrometry can do more than just look at isotopes. It can be used to analyse organic and inorganic substances, and that will be something that we look at in another video. But in this one today, we are primarily looking at isotopes, or considering isotopes and mass spectrometry in relation to isotopes. We will very briefly at the end look at some basic analysis of organic substances, but our focus today is on isotopes. So, like I've said right at the beginning, AQA is only really interested in time of flight mass spectrometry, and there are 4 stages to time of flight mass spectrometry. So we're just going to list them here, and then we're going to go through them one by one. So the first stage is ionization. The second stage is acceleration. The third stage is ion drift, and that is really where this version gets its time of flight name from, because we're measuring the time of flight of that drift. And then the final stage is detection. So how is it we know that we have that particular isotope and the relative abundance that we believe we have? So the first stage is ionization. There are 2 methods we have to be aware of how we ionize our sample. In both versions, we must have it in a gaseous form. Okay, so the first thing that we do is we vaporize our sample, and we make sure it's in the gaseous state. Okay, so once our sample is vaporized in its gaseous state, and it's now in the ionization part of the mass spectrometer, in most of the molecules or atoms that we'll be considering, the way that we ionize that particular particle is by firing high energy electrons at it, right? So there's something called an electron gun, which is just simply a sort of hot wire filament, and that fires high energy electrons at the sample, and in doing so it knocks off an electron from each particle of that sample, and we create 1+ ions. Now, this ionization is crucial, because without it we won't be able to accelerate our sample so that we can get information about it. So the bottom right hand corner of this page shows us some example equations representing the ionization of our sample. So our sample just hypothetically is X. It's gaseous because that's what we've done, we've vaporized it, so it's a gaseous sample. We knock an electron off, so we make a 1+ charge gaseous particle, and of course we have to balance our equation Every equation must be balanced both in terms of the numbers of each element, but also in terms of charge. So we've got our plus electron there, and if you think about it, that's exactly the same equation as for the first ionization energy, although that's not what we're looking at here. Once our particle is charged, then we're going to be able to accelerate it. We're going to talk about that separately, but you'll see that it's being accelerated by a negative electric plate. So that is why we need the sample to be ionized to have a positive charge. And for very large compounds, and so the example here are proteins, and proteins are absolutely huge, it's ionized in a different way. We have our sample in a volatile solvent. So volatile just means it's something that evaporates easily. So we have our sample in a volatile solvent there. And we have then that sample in the solvent pass through a hypodermic needle attached to a positive terminal. Right, so this is all it's convoluted. So a positive terminal of a high voltage power supply. And this time, instead of knocking an electron off, what we're in fact going to be doing is adding a proton. And if you think about what a proton, how we can do that, well, an H plus ion is a proton. We've knocked that single electron off the outside one of the first energy level of the hydrogen. So we just have a proton left behind. So we are just adding a H plus ion to our sample, thereby making it a charged particle. We've got to bear in mind that its mass number is now going to be one greater than its actual mass number, because the mass number of that H plus is still 1. So if we discover that the mass of our protein is 1001, and we'll understand a little bit how we know what its mass will be based on this method. But if we know it's 1001, then we've got to bear in mind that its true mass was 1000, because the 1 came from the mass of the H plus ion. Again, though, once it's ionized, so it's only the method of ionization that's different. When we have a very large compound such as a protein, it's still being ionized so that it can be accelerated by a negative electric field. So the vast majority of mass spectrometry ionization is the previous version, where we fire high energy electrons at a sample and knock an electron off. But we do just have to be aware of this different method here, spray ionization, and it has once come up in an exam, so you mustn't ignore it. But most of our focus and most of the questions that you see, so just remember that as well, bear that in mind, will be about high energy electrons knocking an electron off. But don't forget about spray ionization. So we have our ionized particles. An electric field then accelerates these particles, and then absolutely crucial to this, to time of flight mass spectrometry, is that the ions are accelerated so that they all have the same kinetic energy. That is the crux, that is the fundamental point of time of flight mass spectrometry, that everything that gets accelerated will have the same kinetic energy. So we have to recall our kinetic energy equation that you would have done at GCSE in physics. So kinetic energy is half mv squared. Remember that m is mass and v is velocity. Bear in mind that this is a physics equation. So because this is a physics equation, we will be using the units, we'll be using the conventional units for physics. So in chemistry, we use grams, okay, moles. When we talk about molar mass or the mass of 1 mole, we're thinking about the grams of a particular substance. In physics, when you're using mass, you're talking about kilograms. And we've got to be very wary of that when we're doing actual calculations. And obviously we'll talk about that, but we'll do that probably in a separate video when we look at some sample questions. And then, of course, the units of velocity are meters per second, and energy here is measured in joules. So we have our kinetic energy equation, and we can rearrange it so that we get it in we can have velocity as the subject, if we wanted to know what the velocity was, it would be the square root of 2 times the kinetic energy over mass. That ability to rearrange equations to make the subject the thing that you're interested in is very, very important in exam questions. So that's something you need to make sure that you're comfortable with, that you could convert that kinetic energy equals half mv squared equation into, say, the version beneath it where it's in terms of velocity. So once the particles have been accelerated and they now all have the same kinetic energy, they then pass through something called the flight tube. Because they've got the same kinetic energy, but they're going to have different masses, because that's what we're determining, aren't we? We're determining the fact that there are these different isotopes, and if there are different isotopes, then they have different masses. Then that will mean that their velocities are different, and if their velocities are different, that will mean the time that they take to travel through the flight tube will also be different, and that's how time of flight. This is the time of flight part, of a time of flight mass spectrometer. So you remember that we rearranged the kinetic energy equation on the previous slide so that it was velocity equals, and it was the square root of 2 times the kinetic energy over mass. Well, we've got here, we also know that velocity is the same as, or is distance over time, because those were the units, weren't they? They were meters per second, and meters is distance. Time is measured in seconds, so meters per second is distance divided by time. So we can substitute that into our equation that we had on the previous slide. So now we know that distance divided by time equals the square root of 2 times the kinetic energy over mass. We can now rearrange this equation, this expression, so that we have time as our subject, and that would be time equals distance square root mass over 2 kinetic energy. I've made quite a few sort of jumps there, so one thing that would be very important for you to do at this point is to make sure that you are happy to get from 1 to 2. Okay, so make sure that you're happy to go from the first expression to the second expression. Okay, so all of our ions have entered the flight tube at the same time, and they all have the same kinetic energy. And we know from the previous slide that we could come up with an expression where time was equal to the distance times the square root of the mass divided by 2 times the kinetic energy. And we can simplify that. So one of the things I hope we can see that they're all going through the same flight tube, so the distance is a constant. We also know that the kinetic energy is the same for all of the particles, so the kinetic energy is a constant, and of course 2 is a constant. Now the consequence of all of that is that we can say that the time that it takes for each particle to travel along the flight tube is proportional, that's what that symbol there is proportional to mass. So what we can clearly see from that expression is that the greater the mass, the greater the time it takes for the particle to travel along the flight tube. So in this illustration here, we've got 2 particles, one with a mass of 35, one with a mass of 37. They are setting off along the flight tube at the same time. They both have the same kinetic energy. The kinetic energy is related to mass and velocity. So the 37 clearly has a greater mass than the 35 particle. That must mean that its velocity is less if they're to have the same kinetic energy. But as we've seen anyway, that time is proportional to mass. So as the race gets started, 35 is travelling at a greater velocity. So they start to separate out because they're travelling at different velocities. And eventually 35, the particle here with a mass of 35 will reach the detector before the particle with a mass of 37. And that's how we've been able to separate them out, but also because we know the kinetic energy that's been supplied, or we would do in this, because it's a time of flight mass spectrometer, and we can actually work out what their masses are. We will be able to work out that it's 35 and 37. We wouldn't have known that at the beginning, but because of the time of the flight, because we will know the kinetic energy, or the machine will know the kinetic energy that's been supplied to them, it would be able to work out the masses of those respective ions. Equation. Oh my God. So we have a positively charged ion reaching the end of the flight tube. At the end of the flight tube is a negatively charged electric plate. So you can just think of it as being like there's a lot of electrons on the plate there. So when the positively charged ion hits that negatively charged electric plate, it accepts or gains an electron, and then that is going to result in a flow of charge, and we know that flow of charge is what a current is, an electric current is, and we can measure that electric current. So that's how the detection happens. So we know that a particle or a particular type of particle has hit the detection plate at a particular moment in time. We know how long the flight tube is, so based on that we could work out the mass of the particle. But not only that, there might be a lot of one type of particle, there might be very few of one type of particle, and so the size of the current is going to give us a relative measure of the number of ions hitting the plate. So we've got a current flowing, that's going to tell us that we've detected something, and then the size of the current is going to be proportional to the number of ions that hit the plate, so how many electrons were effectively accepted, so that's going to give us, that's the size of the current. So from all of these things we get quite a lot of information regarding the sample that we put in right at the very beginning of the whole process. And what we get as a result might be something like this. So we have a graph, and if you look at our y-axis, it says it's m over z, okay? So we just need to make sure we understand what that means. So if we write m over z, the m is mass, and z is charge. Now, typically, or at least the way that we've described it so far, is we've always described it as knocking off one electron. So we have always been talking about a +1 charge. And therefore, if you're dividing anything by 1, then we know that in this particular example here, our mass is going to be the values of these numbers, 63 and 65, assuming, of course, that the charge is 1 plus. Okay, and it is 1 plus, but we just have to be wary of the times when it could be 2 plus, and so that would give a value that was half the mass, or half the actual mass. Anyway, what we can see here is that copper, we've got 2 peaks. All right, so we've got a peak at 63 and a peak at 65. And these peaks are giving us a measure of the relative abundance. Okay, so what we can see here is that copper 60, there are 2 isotopes because there are 2 peaks, and that the smaller of the 2 isotopes, so copper 63 is more abundant than copper 65 because we have a higher peak. All right, so we're getting the relative abundance here. Now we can use that information to work out the relative atomic mass of the element. So here's an example of how we do that using our old friend chlorine. So chlorine exists as 2 isotopes, chlorine 35 and chlorine 37. So that's why we have these 2 mass to charge ratios of 35, 37. I think actually those 0.0 shouldn't be there, but anyway, let's not worry about it too much. And then the relative abundance for these 2 isotopes was 75% of chlorine was chlorine 35 and 25% of chlorine was chlorine 37. So if we want to work out a weighted average, or our AR, that is what our AR stands for, our relative atomic mass, okay, so our relative atomic mass, then it's going to be the mass of the isotope, so 35.0 times its relative abundance, sorry, so I'm not going to assume it's a percentage for the moment, so but anyway, times 75. And then plus the mass of the other second isotope, 37, times the relative abundance, 25, divided by the total abundance. So if it is as a percentage, it will be divided by 100, but there will be questions, so you just got to watch out for this, where the relative abundance does not add up to 100. So you just have to be aware that what you're putting at the bottom is the total abundance. So We work that sum through and we get a relative atomic mass of chlorine of 35.5. That's fairly straightforward, okay? And you may well have done this very calculation at GCSE. Of course, it's going to get a little bit more complicated than that at A level. So we're just going to look at neon. So you can see that we've got 3 peaks. So we have 3 isotopes. These isotopes have mass of 20, 21 and 22. We can clearly see which one is the most abundant, the one with the mass 20, and we can see the least abundant is the one with the mass 21. Now I need to give these actual values, so I'm going to give the values. So the relative abundance of neon 20 is 90.9. Of neon 21 it's 0.26, so I'm not sure this is terribly to scale. And then the relative abundance of neon 22 is 8.80. Okay, so now we work out the relative atomic mass of neon. So that's what we're trying to work out. And we've got one isotope of 20, and we have an abundance of 90.90. We have another isotope of 21. We have an abundance of 0.26. And then we have a third isotope with a mass of 22, and we have an abundance of 8.80, and then that's got to be divided by the total abundance, so we're just going to put 90.90 plus 0.26 plus 8.80. When we put all of that into our calculator and do our calculation, we get an answer of 20.17. Of course, our periodic table at A level is to 1 decimal place. So to 1 decimal place, it is 20.2. Here's another example. It's done exactly the same thing. There is a relative abundance here of, that's a percentage that adds up to 100%, so we can just divide by 100. I'll just let you just pause the video and just check you're happy with the calculation. Now, 2 elements that feature quite prominently in exam questions are bromine and chlorine, and we're going to consider why that is and how we can approach those questions now. It's really actually because they exist as diatomic molecules. That's the chief reason, the main reason. So it's bromine 2 and chlorine 2, of course. So bromine has relative abundances. It has 2 isotopes, sorry. It has bromine 79 and bromine 81, and their relative abundances are both 50%. And chlorine, we've already seen, we've got chlorine 35, 75% of all chlorine is that, and 25% of all chlorine is chlorine 37. And the spectrums involving these elements can actually be more complicated than what we've seen already. This final point here, sorry, perhaps should have had this a little bit later. I may repeat it a little bit later, but just bear in mind when you do come to organic chemistry and you come to organic molecules, so molecules that have hydrogen and carbon in them, there are very low abundances, but you can have hydrogen 2 present rather than hydrogen. So you could have one of those hydrogen atoms in a organic molecule could be hydrogen 2 rather than hydrogen 1, or it could be carbon 13 instead of carbon 12, and so you do get these very small peaks, very tiny peaks just to the right of the bigger peaks, mainly, well, basically because of the existence of these isotopes. But that's a slight aside. What I want us to focus on now are the spectra for bromine and chlorine, which are a little bit more interesting than you might have originally thought they might be. So if we were to do mass spectra of bromine in a time of flight, we would mass spectrometry, we would actually get 5 different peaks. Now, in terms of their heights, I want to split them into 2 groups. Okay, so they are not all to be compared with each other. What we can do is we can compare these 2 peaks with each other, and we compare these 3 peaks with each other. But what we're not doing is comparing the right-hand set with the left-hand set. So bromine exists as 2 isotopes, bromine 79, bromine 81. So when we look at the left-hand set of peaks, the left-hand circle, we can see that their relative abundances are the same. There's a ratio, there's a 1-to-1 ratio, and they had a relative abundance of 50% each. When we look at the right-hand set of peaks, these refer to the diatomic version of bromine, so Br2, the original, I suppose, that we would have been injecting into the mass spectrometer. And we get 3 peaks, and that is because we can make up that bromine, Br2, sorry, using those 2 isotopes where we can have, oh, there's a mistake there. Let's just correct that. So where we have 2 bromine 79s bonded together, or we can have a bromine 79 and a bromine 81 bonded together, or we can have 2 bromine 81s bonded together. So I don't think you necessarily find it unreasonable to know that there are going to be 3 peaks. So we've got, because there are 3 possible variations of the 2 isotopes coming together. What we do have to consider, though, and what perhaps is maybe a little bit more surprising for you, is the fact that we have the ratio of 1-to-2 to 1. So we need to understand why it is that we've got twice as many bromine 79, bromine 81 molecules as we have bromine 79, bromine 79 molecules and bromine 81, bromine 81 molecules. And the way that we understand that is in terms of probabilities. So I've just drawn this table up in the top right, and the way we're going to approach it is, well, what if I was taking these atoms from a bag? So I have a bag of bromine 79s and bromine 81s, and because I have a relative abundance of 50% of each, half the atoms in my bag are bromine 79 and half the atoms in my bag are bromine 81. So, and I'm going to draw out 2 atoms. So I could draw out a 79 and then a 79, or I could draw out a 79 and then an 81, or I could draw out an 81 and then a 79, or I could draw out 2 81s. So it's important to think of them as being pulled out one at a time. So when you look at this, you can see that we have there are 4 possibilities. One possibility is bromine 79, bromine 79, but there are 2 possibilities of having a total of 160, of having an 81 and a 79, right? So there are 2 possibilities there. And then, of course, we have 1 possibility for 2 81s. So this is why we get that ratio of 1-to-2 to 1. Okay. Okay, so how about with chlorine? So as I did with bromine, I want to split it into 2 sort of sets of peaks. So we have this set of peaks on the left, we have this set of peaks on the right. And I just want to compare the peaks within those sets. Now we know already that this chlorine 35 is 75% of all chlorine and chlorine 37 is 25%. So we can see that 3-to-1 ratio. We can understand that we have 75% abundance of that and 25% abundance of that, and that would give us a ratio of 3-to-1. When we look at the second set, the one on the right, this is when it's the diatomic molecule, we now have this ratio of 9-to-6 to 1. And so we need to appreciate and understand why it is those ratios. So I'm going to do something similar to what I did before with bromine. I just need to allow myself a little bit more space. But I wouldn't mind you just pausing the video and having a think about why it is that we get that 9-to-6 to 1 ratio when it's the diatomic molecule of chlorine. Okay, so I've drawn a similar table to with bromine, although it is a little bit more complicated. So one thing I want to just point out is that I've changed the 75 and 25% to 3/4 and 1/4. And these are the probabilities that when I take an atom out of my bag of chlorine atoms, There's a 3/4 chance that it'll be chlorine-35 and a 1/4 chance that it'll be chlorine-37. So again, I'm going to draw out two atoms, and I'm going to look and consider the probabilities of what combination I get. So I could draw out chlorine-35, it's a probability of 3/4, and another chlorine-35, which is also a probability of 3/4. And so the overall probability of that would be 9/16. I could draw out a chlorine-35, and then I could draw out a chlorine-37. So the overall probability there is 3/16. I could draw out a chlorine-37 and then a chlorine-35. So that would again be 3/16. Oops, sorry. And then finally I could draw out two chlorine-37s, which is 1/16. So when you look at that, you can see there are two possible ways I could have drawn out something with a mass of 72, i.e. something with a chlorine-35 and a chlorine-37, just as before. Those combined probabilities would have been 6/16. So we have a 9:6:1 ratio. Now that's something for you to maybe sit back and think about and make sure you're happy with that consequence. And if you're not, just please let me know, okay? There's just one more thing that I want to reiterate, and that is to really remind you that the x-axis is an MZ value, so it's a mass over charge value. So for anything to be detected in a mass spectrometer, it must be charged. Okay, so whenever they ask you what is the species responsible for the peak at something, such and such a thing, they've used the word species because they don't want to give you a clue that it's an ion. You have to recognize that it must be an ion. So if they asked what is the species responsible for the peak, it's 74 in this mass spectra, it would be 37 Cl2. Okay, so we'd have the 37 mass number, Cl, and then subscript 2 because it's the diatomic molecule. So please just remember that an MZ value is mass over charge. So you must have a charged particle if it's to be detected in a mass spectrometer. So we're just going to end on relative molecular mass, MR. So mass spectrum can be a way of finding the MR of a compound. So this is to do with organic chemistry. So you haven't quite done organic chemistry yet, but it'll be something that you feature, and you have done MR before at GCSE. So here we're going to be considering the peak that's furthest to the right. So that whatever the peak is furthest to the right is clearly the peak with the highest MZ ratio. And that will be the molecular ion peak. So that will be the peak that corresponds to the molecule. So it's one way of discovering the mass of the molecule, or that you've put in that the sample. So you may not know the mass of the molecule that is your sample. So you can use mass spectrometry to do that. You'll just notice on the equation at the bottom, I've got something that's a little bit different than earlier. I've got, let's see if I can better highlight it. I've got this dot here. Okay, so that's representing a free radical. Okay, and that will make more sense once you've done the alkanes topic. But essentially, in an organic compound or in an organic molecule, every electron is paired up. It's either in a covalent bond or it's part of a pair of electrons around an atom that isn't taking part in bonding. Now, if you knock an electron off and every electron was initially paired, then you must be knocking an electron from a pair, or knocking one of the electrons of a pair out, which means that you're left with a single electron somewhere on the molecule. Now, single electrons in organic molecules are called free radicals, and so we have to represent that really in our equation. So our M represents our molecule. Of course, it's gaseous again because we have to vaporize our sample before we put it into a mass spectrometer. we fire high energy electrons. It's obviously a small molecule, so fire high energy electrons at it. It knocks an electron off. That makes our molecule now positively charged, but we have to show that we also have an unpaired electron, which is what the dot is there to do. It's a free radical, and the whole equation is balanced. So here's an example mass spectrum of a simple organic molecule, so ethanol. So we know the molecular formula is CH3CH2OH. That has an MR. If we were to do it using our periodic table, we would discover it was 46, and so that's what we get. The peak that's furthest to the right in our spectra here is 46, and that is the MR, right? That's the molecular ion peak. We have some other peaks present. So it's this word here, fragments. So the fragments here, basically what happens to an organic molecule in a mass spectrometer is it can be broken up. So if you can think of, you've made something out of Lego, but you maybe snapped it in a couple of places, they would be the fragments. C15 would be the CH3 if it broken there between the CH3 and the rest of the molecule. 29 would be CH3, CH2. Of course, these are going to be charged. Okay, so let's remember that. 31 would be CH2OH. Could be that part of the molecule. I'm not sure about this 18, so I tell you what, I'm just going to scrub that. But anyway, so that's how we could use the information to learn a little bit more about an organic molecule if we were to put it into a mass spectrometer. But that is something that that's something that's going to feature much more when we do the organic part of the course. So I'm just introducing it here because it is about mass spectrometry, but we will do more about mass spectrometry in the organic analysis part of the organic side of the course. So that's mass spectrometry. I'm going to do another video, a separate video that looks more closely at some example questions, particularly ones that are that stretch you on the mathematical side of the course. So look out for that, and yeah, ask me if you've got any questions at any point.